Whew, all right. So we did a quick overview of the three. I ran through an example of the stack and the heap. Let's go ahead and jump back to static. Did you have a question? Just stretching? Perfect. So static is the simplest storage. Notice that that's where your code is and whatnot. Actually, in this picture, I said the OS is part of static. Not exactly true, but that's all right. It's your code. It's also any global variables or constants, because those are going to exist throughout the entire lifetime of your program. So global variables are also up in the static area. We don't have any global variables in our code right now, so I don't have an example. But your code definitely is part of the static. The stack is the runtime. It automatically grows, allocated when the activation record or stack frame is pushed at the time. Wow, that's a complicated way. Every time you call a function, it allocates memory on the stack and then uses it. It shrinks when the method terminates, so it automatically deallocates it. All right. One nice thing here. Did any holes ever appear inside the stack? No, because it always grew and shrank at the end. That is a very nice feature. That is a wonderful feature. Okay, we went through that. Great. Heap. Oh, just for clarification, what's the lifetime of a variable on the stack? Yeah, the function. So, there we go. Notice that when double add was called, this A, its lifetime was still, while you're calling the other add function, you just didn't have access to it when you're inside of this function, right? But this variable was still alive because it was still, because it was still allocated from the stack or on the stack. But once the function was called, its lifetime ended. We killed the variable, basically. We deallocated it. Murdered it. There's going to be a lot of that. Yes, I'll just stick with that. Heap. All right, allocate, deallocate dynamically as the programs run, not associated with any function or context. Okay. So here's the quick little problem. If I go ahead and end this function right here, the stack pointer will go ahead and jump up actually to here because we return from main. And then the OS is going to say, okay, we're done. Let me deallocate the rest of your static memory. There we go. What's the problem?
Still have allocated heap memory?
Did we deallocate him? No. We didn't deallocate this guy. Java automatically deallocates because when you allocate memory, it actually stores what's called a reference counter associated with it to keep track of if it's been referenced or not. And every once in a while, Java automatically tries to figure out what variables it can deallocate for you. And then when the program ends, it just goes through and cleans it all up. C++ doesn't do that. So you just left some variable out there hanging. That's called a memory leak, because you're leaking memory that should have been deallocated. Now, modern operating systems, when your program ends, will automatically deallocate the memory. But if you're running a program yourself and you need to run it for months and you're leaking memory, you will eventually run out. Okay, different policies. So we talked about new and malloc. That's what we use, free. There might be holes. All right. So what are these holes that it's talking about? Well, let's go make another function. I don't know why I wrote it like that, but it sure did. Holy? Yeah, okay. Int A equals new int. Hey, let's put in a bracket of 100. What does that mean? Yes, so we are allocating 100 integers on the heap. So it would just start down here and then go up 100 times 4, 400 bytes, and then give you the memory address of where that began. This is a contrived example, but I wanted to show you the problem. I'm not going to write all of this again over here. That would just take me a long time. Let's just go and give the heap memory right here. So you got 100 ints down here, right? And that's what we're going to have A. And A is pointing to right here. There's a memory address associated here. That's what's being stored in A. Hopefully y'all see this so I don't have to write it out again. Then you have B. And we're going to also have 100 ints. It is hard to write sideways. And B is going to go right here. And then we're going to have C. And it's going to point to the next one. Okay, and we are right here. Everyone with me so far? A, B, and C are on the stack. They are pointers, so they're 8 bytes each. Each of them are pointing to a different set of 100 integers. When we delete B, we are deallocating this right there. Now, notice B still points to it. We've just deallocated it, okay? And I'll just put a big D right here, just so you know it's been deallocated. So when we go to B to create new 200 ints, where are those 200 ints going to be allocated?
There's not enough space for it to be put there.
Right, so it needs to be up here. Is that a problem? So one solution is to copy all this down and then update all your pointers. That takes a very long time to do because you have to copy memory. Memory is the bottleneck of your machines. It's one of the slowest operations, unfortunately. And then you have to go through and find all your pointers and update them accordingly. How many people want to write that code? No one. No one wants to write that code. The computer does not do that for you. But good guess. I mean, that would solve this problem. It would. That would definitely solve this problem. The computer doesn't do this. Why is this a problem? Well, what if you had so many holes and then you wanted 200 integers, but there wasn't a hole big enough to allocate it, even though you had plenty of open space? So this is called fragmentation. Because you fragmented your memory by putting in so many holes that you no longer can allocate the memory you need anymore. Doing good? Okay. That's leaving holes, aka fragmentation. Perfect. So in C++, notice I had to use the delete command in order to deallocate it. Java did it automatically for you. Perl, Python, Lisp or Lisp-based programs. A lot of other programs have garbage collection to reclaim the unused heap space. Why did C++ not put in garbage collection? It could have. There are libraries to do it, but it's not part of the language.
It's old.
Because it's old. Good guess. But C++, that would be a good answer for C, because that was 1970. But C++ came out much later when garbage collection was well known. So why did C++ in particular not add it in?
It makes it slower.
It makes it slower. That's correct, in a way. It's a trade-off. By having a garbage collector, what happens is your program's running, and then your language stops. Everything you're doing goes, checks to see if it can collect any garbage, and then jumps back to your program. So it's constantly stopping, cleaning up, and then going back, which is a performance hint. But in Java, depending on what you're doing, it may or may not matter. For a lot of programs, the garbage collector just makes your life easier and the performance doesn't matter. If you're writing an operating system, that performance is going to matter a lot because no one wants their kernel or their OS to start slowing down. So it's ups and downs. By having a garbage collection, you have a harder time predicting how long something takes because it's going to stop. But then you don't have to deal with delete, which, by the way, would be very nice, but it is expensive. Hey, look, that whole picture that I made just up there. Great. Question, what happens if the stack and the heap meet?
You're out of memory.
You're out of memory. All right, stack overflow. So if the stack tries to flow into the memory, it's a stack overflow. Or I'm sorry, if the stack tries to flow into the heap, it's a stack overflow. You're out of memory. And the other way is basically just out of memory heap. When you call new, it returns null, and then you don't have memory. All right, so the new return start address of a block of unused heap storage. Hey, it does exactly what I did up there with integers, just showing you with arrows. Perfect. Excellent. Heap overflows when you can't do it anymore. Correct. So we have delete, and that's down here. I put in a D for delete or deallocate. So that's how you get rid or deallocate the memory. All right, pointers. We just use pointers. If there was any way I can make you instantly understand pointers, I would do it, but they're very simple, but are going to be quite deceptively complex. Pointers are addresses. The value of a pointer variable is an address. I'm going to iterate this so many times, I hope it's like beating a dead horse. D is a pointer. It is on the stack. Its value is a memory address. The value of a pointer is a memory address. What's the memory address? It depends on what it's pointing to. The compiler knows it's pointing to an integer, so it jumps to this memory address and treats that as an integer. If I made this a double, it would treat this as a double. If I made it a character, it would treat it as a character. If I made it a special object, it would treat this as an object. But the pointer is always holding a memory address. The value of a pointer is always a memory address. Or is treated, I should say, as a memory address. The value of a pointer is treated as a memory address. Because we're about ready to get into some wackiness. Java doesn't have explicit pointers, but they're called references, which are basically a pointer. All right, memory allocation, Java versus C++. Java can't do a couple things, by the way. So, stack. You want to put a primitive on the stack in Java. Primitives in Java were your lowercase integer, basically everything that started with lowercase. Int A, heap example, new int, but this is actually an array object, but that's okay, we'll go ahead and leave it this way. Stack example. In Java, you cannot put the instance of a class on the stack. You are never able to put an instance of a class on the stack. You had to always create it on the heap. So the top example was Java. Down here is C++. Again, primitives. Hey, look, it's just like Java. Int. It's similar to Java, except for instead of doing this array brackets, we did a star. You want to put a class. Let's skip the class example. And this needs to have a pointer right there. Ooh, that is bad. Oh, that is so bad. We need to fix that now. Boom. Okay, much better. So notice on the heap side, you always have a pointer in front of it, a star. New string, there you go. Notice that if you do not put the pointer on it, it creates it on the stack. Hopefully this horse is going to die. I mean, it's gone, because I'm trying to make this simple. Pointer, star, str, it would point to the object down here. If you did not put a pointer, it would put the object information here on the stack. Why is that nice? Ooh, why would that be nice? When does it get deallocated, I should say?
When the function ends.
When the function ends, it's automatically deallocated as opposed to you having to delete it manually. How we doing? Okay, let's see. Java arrays are always allocated from the heap, great. Dynamic allocated also have storage, great. All right, that's fine. We're gonna skip that for now. We talked about that a lot. We talked about garbage memory leaks, we did, garbage collection. Okay, let's go and do some code because I'm kind of tired of talking. We'll call it pointers 1. All right. Go ahead and include our good old IO stream, main int argc char star argv. Hold on a second. Okay, so we have int a equals 4, int, we'll go star I equals new int, star I equals 5, and then we'll do it cout I equals. All right, what should that print? What is I?
A pointer.
A pointer. So what is it going to print when I print out I?
Memory address.
It's going to print out the memory address. Yeah, that's a memory address. Hey, it even started with 55. Good job, whoever told me that. All right. But if I dereference it, it should then do what?
Show you 5.
Yeah. And then 5. Perfect. Hey, let's Valgrind this thing. Definitely lost. What happened?
You didn't delete.
We didn't delete it. Isn't that nice of Valgrind to tell you? That's very nice. Oops, wrong button. Everything freed, we're good to go. All right, hopefully nothing too crazy going on. Ooh, what does that do?
Does it reference the memory location of A?
Yes. So what is I going to hold?
Memory location.
Right, the memory location of A, and then when I dereference I, what is it going to print out?
The value of it.
Which is 4. Okay. What's A going to be? Say it.
20.
20. Why is it 20? I is pointing to A because it has a memory location of A. Therefore, if you dereference I and store 20, you're changing A's value. How are we doing? All right. Let's see, what would be a good one here? Trying to think of an easy example. And I don't want to call it sum, because we already did that. I would call it set. Oh, it is burning up in here. Whew. Yeah, let's go do that. What do I want to put in here? 20. Yeah. Thank you. Just in the middle. Good. I think it's slightly cooler. All right. Okay, set 2x. What am I passing? The first thing I'm passing is the, what am I passing?
Memory address.
Memory address of A. And the value 20. Let me change that because I might confuse what's going on. So let's change that to 25. So when it calls it up here, num or part num is actually pointing to which value?
The memory location of A.
Correct. It's pointing to the memory location of A. And what value am I passing to Val? 25. So what is this doing right here?
Did you dereference it?
I'm going to dereference that value, so num is actually going to hold where A is, and then I'm going to set it equal to 2 times val, which would be 25. So after calling set A should now be 50. Notice that this is another way to pass a variable to a function so that you can change it. This is how you can change a variable that you pass to a function inside of C++. In Java, it was implicit because whenever you passed an object, you were passing a pointer. It just didn't call it a pointer. Here, you have to be explicit about when you're passing a pointer or when you're creating a copy. And I'm going to change a couple things up here. I'm going to go ahead and create int b equals 25. I'm going to go down here and make that a b. And then I'm going to say val equals 2 times val. And I'm doing this to drive home the point. So what is, let me comment out those top two things. All right, so what should A and B both be at this moment? I'm going through this exercise because this is how your homework is going to look. I'm going to give you code, and you got to figure out what the values are. Some of it you can type out, some of it you're not going to be able to. So what's A going to be? I think we went, oh, let me, there we go. I think we said that. A is going to be 50, and what's B going to be?
25.
25. Why is it not 50?
Because you made a copy.
Right. Because a copy was made on the stack when you called set 2x, and therefore the B that's a member of main was not manipulated because you weren't passing a pointer to it, you were manipulating the copy of it. All right. How are we doing? Doing all right? All right. All right, so we have the 3 different ones. Ooh, dangling pointers. Let's talk about that. So I delete I. Is this okay?
No.
This is actually okay. Good guess, though. It's okay because it's only storing a memory address, right? I'm just printing off the memory address that I had before I deleted it. That's okay. There's no problem there. See, we'll even run it under Valgrind. And Valgrind will be like, you're still good. Is this bad? This is very bad. Is it going to throw an error? It didn't. gave us a bogus number, aka it's undefined. All right? That should have caused an issue, but it did not, because you were still within the bounds. All right, technically you were in bounds, you were within the bounds of the segmentation of your process. When you take OS, that'll make way more sense, but just notice that sometimes it will not give you a problem, and other times it'll seg fault. Seg faults are great because then it caught the problem. Not seg faulting when there's an issue is bad because you didn't know that something messed up. Oh, but on the flip side, let me go and recompile. Let's run it under Valgrind. Oh, invalid read of size 4. Isn't that nice? All right. So, what is I? I here is called a dangling pointer because it's still pointing to something that you deallocated. It's dangling. It shouldn't be pointing to that. So, the simplest way to keep yourself out of trouble is after you delete, do that. All right? Why? Because when you do that and you run it, you will get a segmentation fault. And then you know that something bad happened and you can run the debugger or Valgrind and figure out where it happened. But I'm going to leave that out for now, just to show you. And we talked about memory leaks. Great. We talked about that. And okay, that's good for now. All right, how are we doing? We're going to visit pointers again. Let's go ahead and go to your lab. Unfortunately, I'm not going to double time it because that'd just be mean, but we do need to, pick up a little slack since we missed a whole week.